Hello. In today's presentation I'll be talking about MAT, a new multimodal system for remote attention level estimation based on multimodal face analysis developed in the BITA lab of Autonomous University in Madrid. Virtual education technologies are growing, with a market reaching a turnover around $370 billion in 2026. E-learning platforms are important tools to get high-quality online education. Information such as heart rate, emotional state, or cognitive activity can be used to improve these platforms. How can we estimate the attention level? Brain waves from an electroencephalogram have demonstrated to be one of the most effective signals for attention level estimation. However, this method is very intrusive and it requires sensors such as headbands or electrodes, etc. More realistic methods to use in e-learning environments are face videos obtained from a simple webcam, which are less effective nowadays. Human behavior generates useful features to assess the attention level, related to students' pose, students' facial expressions, distance between students' face and screen, eye blink. For example, the eye blink frequency is related to the cognitive load. Lower eye blink rates can be associated to high attention levels, while higher eye blink rates are related to low attention levels. This work implemented both methods. The main contributions of this work are: firstly, we performed an attention estimation study in a realistic e-learning environment, using different modules based on convolutional neural networks, trained to obtain facial features with potential correlation with attention. We evaluated each module in the attention estimation task. And secondly, we proposed a multimodal approach to improve the estimation level results in comparison with a monomodal system, and we compared also another existing attention estimation system called ALEBK, both evaluated on the same mEBAL database. The mEBAL database was captured in a controlled environment where the activities performed by 38 students were carefully designed to detect different attention levels. To capture mEBAL, we designed a multimodal acquisition framework to monitor cognitive and eye blink activity during the task execution. It used two sensors. First, an EEG headset by NeuroSky, to capture the cognitive activity of the student. Second, an Intel RealSense including one RGB and two near cameras. Our approach employs face videos obtained from the student's webcam. First, we use the face detector module to obtain the face's position. Afterwards, we apply modules specifically trained to obtain facial features like head pose estimation, facial expressions, landmark, and eye blink detector related to the attention level. For each feature vector we train a binary classifier, low or high attention, based on a support vector machine using as ground truth the obtained attention level by the band. Each of these SVMs are evaluated as binary monomodal classifiers. The attention is estimated every second based on the features captured during the last minute. Finally, a multimodal system is proposed. We combine the scores obtained from each of the facial analysis modules based on a sum. We used a landmark detector to obtain the following features: the eye aspect ratio for each eye, which is related to the opening of them; the width and length of the nose and head as features to detect the head distance from the screen, and it is based on VGG16 plus 2 convolution layers. The head pose estimation module was used to obtain the vertical and horizontal angles features that define the 3D head. This module used a single convolutional neural network. The eye blink module was trained on mEBAL from scratch. This detector has been inspired by the popular VGG16 neural network model, and it's a binary classifier, sorts open or closed eyes using as input left and right eye images. For the region of interest localization, we applied face detection, landmark detection, face alignment, and eye cropping as we can see in this image. The obtained feature from this module was a scalar value between 0 and 1 for each frame. The facial expression is based on FaceNet and was retrained with Facial Expression Comparison by Google. This module was used to obtain a 16-feature vector per image that defines the student's facial expression. Instead of trying to predict the exact value of the attention per second as the EEG band obtains, we believe it is possible to predict high, low sustained levels of attention over 1-minute periods, using webcam images exclusively. This figure shows the probability density function of the attention levels provided by all mEBAL students. The main goal was to detect periods of high and low attention levels, That's why we defined two symmetric thresholds, for the highest and lowest levels, 90% and 10% respectively. We obtained 3,706 1-minute samples from mEBAL database with balanced samples. This table shows the accuracy results for each monomodal approach evaluated over the mEBAL database. We used the leave one out cross-validation protocol. The results showed that modules based on eye blink and facial expressions obtained the best scores, close to 76% and 67% accuracy respectively. Also, we discovered that high attention levels are easier to recognize than the low ones, which have a more expanded density distribution. This table shows the accuracy results from the best combinations of the proposed multimodal approaches using the mEBAL database. The head pose module showed the second worst monomodal results. However, when the head pose is combined, it improves all the combinations where it's included. It shows the capacity of multimodal approaches to improve the methods for attention estimation. The best scores were obtained from the combination of three modules: eye blink detection, head pose, and facial expressions, with an accuracy around 82%. In this chart, we can appreciate the obtained ROC for this multimodal approach, blue line, and for each of the monomodal systems combined. The blink is shown in red, head pose in pink and facial expression in black. As we can see, the ROC improves with this combination. Finally, the results were compared with a new approach called ALEBK. This is an attention classification method, low or high attention, based on the eye blink frequency per minute. It was evaluated over the mEBAL that obtained an accuracy of 70%. The results show how our monomodal and multimodal approaches outperform the ALEBK results, obtaining a 40% of relative reduction in error rates. The results have shown the capacity of multimodal approaches to improve current methods for attention estimation. In future studies, we will explore other features and new architectures that combine short and long-term information. Thank you for your attention. This concludes our presentation with a list of selected references.